So today we'll start talking about machine learning. That's our goal. Basics. But let's talk about, of course, our course in general.
Should it be chapter 18, not 19?
Do you mean?
Should it be chapter 18, not 19?
Yeah, well, let's skip chapter 18 for now.
Okay.
Let's skip chapter 18. It should be multi-decision making, right? You look at the notebook, but we'll skip it for now. Okay. So it might have some relevance to your midterm, and so we'll do that first, right? So we'll play both. I believe it's due today, right? 59, right? So how are we doing? Some of you have pretty good bots already, right? Who can beat the random one, right?
Yes.
But we need a little. I'm thinking of extension, right? So Wednesday, because I heard some feedback. Somebody might not be available next week, so probably to do the tournament, it'd be good to do it on Thursday, actually, to run it. That's the goal, right?
I have several questions
Yes.
regarding tournament things. So, okay, the first one is we stop at do we need to be present?
No, you don't need to be present, right? But I need some way of running it, right? So I need some way of running your program, and of course, ideally, to be on code spaces, right? So it's common. So some sort of something runs on Ubuntu, right? I think it's way too, but yeah. So, or of course, if it's a script file, right? In Python, of course, or whatever.
So it needs to be runnable in code spaces. Okay.
Yes.
So and the next one, will you improve the server?
Yes. So the thing is, let's see what's missing from specification of the server currently, right? Because ideally, a server will be changed, but the API calls should not be changed. Is there anything missing? Because the idea is this: your task is only call the address, right? Mm-hmm. And you should be getting an ID for the game, basically, right? And that's it, right?
Then
so you should not care what's happening in the server, right? So the only thing that's extra is that start, that basic, the start, which is the basic random bot, basically gives you the random game, right? So what would be nice, but I think would make things easier, if you have an option to provide the address for the starting the game, right? You maybe want to change, right? So you can try different addresses, right? So because maybe your nice little server that runs down, we need to run it somewhere else, right?
That was specified in there.
Yeah, I think I said it, right? So let's double check again what I wrote, what's not working. Maybe there's something I still need to do, right? So the API, so basically this type of address, right? I put the actual, right now currently it says the actual address, right? So this should be specifiable, this address, right? The port, I'm not going to change the port, but the address might want to change something, right? Because especially if you run it locally on code space, right? I would enter 0000 local loop, right? Loopback address, basically, right? So I don't know. So something like this, basically, right? So this could be anything, right? So that would be really a good, easy to add to your code, I'm sure, right?
Wait, I got a comment. So the time is a thing that.
Okay, yeah.
So the first is that it doesn't. Like it returns, I think it returns hard-coded.
240?
Yeah, 240.
Yeah, so that's...
But the second one is that I assume, and that's something I would also need to understand from a logic perspective, that it's time for me.
Yeah, it's time for you. Time for you.
So it's not like...
it's not a global time.
Because currently it is like global time.
Yeah, so that's something, this is on me, right? But you should consider it, right? This is going to be a real time, right? So this means is, of course, right, you should allow some latency issues, right? Don't hard code yourself 4 minutes for your game, right? Again, ideally, you can adjust this time, right? So how much time you have on your side, right? So because again, if you give yourself 240, right, seconds, right? These are seconds, not minutes. Sorry, seconds, right? 4 minutes for the game, right? On your side, it should be adjustable, right? So adjustable IP address and adjustable time, right? Two things.
And time will be a floating point number.
Yes, a floating point number, right? Yeah.
And will you add a possibility to test on a bot aside from a random one?
Yeah, that is the popular request. Right now, the hardware bot, right, would be, again, if you have custom address, probably be something like, what was the address I gave for the, this one here, right? Yes, but yeah, again, there might be another address for a hardware bot, basically. Now, of course, there's no hardware bot at the moment.
If we want, like, right now, I can present my own.
Okay.
Yeah, I can do something else.
You could add. Do you have an address for your bot?
Yeah, I do.
Okay.
Maybe I can also write
Let's
it down.
write that. I'll add it here. Let's write it. So 37.
It's because it's a certificate, but it shouldn't be a problem.
Yeah.
Update it to it.
Now you need to. And of course you need the address. Yeah, the address, right?
Yeah,
Port.
I'll publish it somewhere, but it should be compatible with the same. I basically took your server and added like my binary that it's called.
Okay, super.
And it's not the best, but it's somewhat smarter than random. So
yeah. So now, okay. So question is, so right now it's not working because we need to have what?
No, it's working. You just need to like slash and.
Yeah. So 555.
No. This is
ID.
It's
Just slash.
443.
Yeah. Okay. 443. Right. So start. Start. So we need that. Let's make up an ID. Let me make myself an ID. One, right? Start, right? Right. So I should. Okay. All right.
Yeah.
So this is so if you're asking, you can play against Martins. Yeah. Hopefully beat him.
Yeah.
Okay. Yeah. So yeah, so,
You can post maybe the address.
yeah, I'll add the address here now. Alternative address. Alternative address right here. Let me make copy of this.
No, to just po student ID
If it's down, I don't have any responsibility.
Mārtiņš Tas ir speciāli down 3 stundas pirms deadline.
So it supports multiple users, right?
Yeah. Basically, it runs the like compiled binary for you.
Yeah, each. Okay, good. This is I'll say Martin's. Extra challenge. All right.
Also, while you're editing, I realized that you did not specify how to get the state of the game.
Okay, the idea was that it should be I don't know idempotent, meaning that you should be getting by entering anything, right? You should get it should respond with the current state, right? So I guess using this approach would give you this should give you the game state, right?
That's kind of for making a move.
Yeah, but also no. If you skip, if you don't add these two, that was the idea. I don't know if I wrote somewhere. Basically, the idea restart is okay, but move request. Basically, maybe I'll make an addition, right? So game ID. So this request is all the moves to get you the state. Yeah, that makes sense.
It just wasn't set anywhere.
Yeah, I guess I forgot to add it, but yeah. Making move, getting state. I guess I'll kick up it here. Yeah. Got it here. I guess R2B, I guess, I don't know. So it happens when you numbering things. 2B. be, no, to be, to not to be. So,
2.5.
game state. Right, if you need to, right? That would be a good design, of course, but it should. Of course, you can also make a completely nonsensical move, also, right? That also works, right? That's not as good as so this part here. Yeah. Okay. Of course, same should go for same. So does your server support this?
What?
It should.
It's I just copied. I took your code.
It should copy. I think it should answer. Let me double check. So let me answer. It's not game ID. What's the eight? What's the game?
No, but yours has like 6,000. So there are people.
At least someone's coding.
So I it's like this, right?
Yeah.
Okay, so this will work or not? Yeah, it works. That's how I tested this. I think I remember. So that's the idea. So you can get for a situation. There's a move somewhere here, right? Yeah. And I think I lost, right, at the time.
Yeah, time run out. My implement.
So you did a time, right?
It's changing time.
All right, excellent. Okay. Cool. Also more okay. All right. So now so that is the calculation. So I don't have a problem extending it because I would like to do it on the tournament, basically, right? On the question is, can we run it on Thursday or do we run it on next Monday? So how many people want to run the tournament on Thursday?
I don't care.
To me, you don't care.
Yeah.
So one person wants to run on Thursday because I think Anton, you want to run on Thursday, right? Or maybe not. So Monday.
I can also do it on Monday, but since Thursday for me will be more.
So Monday, I think, because I'll have to probably. Let's do this. Let's put the deadline on Saturday, but so we can run it on Monday, so I have room to test Sunday for testing this, right?
Mm-hmm.
I mean, worst case scenario, of course, is just I have to run manually, basically, right? And that's not fun.
I got another question.
Yeah.
Maybe distracting away from the deadline, but there's written in the third one that your bot should then start a new game by making another start request.
Yes, okay, so that is his idea. We can run it, right? Until it receives a response to stop, I think, right? Yeah. I think here, let me see where I wrote it, right? Yeah, leave. Yeah. So that was, I think that was pretty clear, right? So ideally, you start a program, you have an address, and you should be getting games, right? And then you get leave, you stop, right? So then you should. So a good bot, right? If you're going 9 or 10, right, you should support the syntax, or actually, well, even 7 should support the syntax. Even if you have a really bad, you play random, right? Right? Well, you can't beat my random bot, right? Or you have a fixed logic, right? 5 moves, right? For 7, you have almost no AI. It's still technically AI, even though it's not very smart, right? So if you get leave, right? So that's what I'm saying, because I think I'm sure somebody else will have some questions by now. So, all right. So maybe. No, I could give you also Friday, maybe not Saturday. You have less time. You want Saturday or Friday? Saturday? Yeah. Right. Because you have nothing else happening right now. No exams or anything. Okay, good.
Yeah.
So this will be the best. So where's my calendar?
I think you have to expand. Yep.
This one?
Yep.
Yeah, okay. Right. So 15. Okay.
Legende uztaisīt labāku handling. Just a question, would it be convenient for you if we were to make executable files and you just
that'd be perfect.
Set the flags and
yeah. So I need 2 options. We need the port, right? Basically, the ports, right? And I guess I can leave this you call. I guess if you want, you can keep this hard coded, right? Or so that you can start, right? Or you can make an option. You can just change that too, basically.
Okay.
Maybe, and of course the time limit, right?
Okay.
So I can change to 1 minute maybe, right? Maybe make it quicker, or 30 seconds bullet, right? Bullet matches, right? But of course, but test on 4 minutes, right?
And so will you make like this three ply bot also?
That's what I would like to do, but I have other things happening, so I would really like to do it, right? So, question is when. I know how to do it. Only problem is when, right?
Maybe you can share how to do it.
What's the algorithm behind the 3-ply bot?
I mean, it's just a basic min-max with the alphabet pruning. I mean, it's just a basic thing, right? Yeah. On the paper, right? It's easy to do, right?
Wat is the rest of
But the problem, of course, is that you need a good eval, right? That's something I have not really talked too much about, right? A good eval, something with 2-ply or 1-ply, maybe even with a good eval or good heuristic, right? Could probably beat a really bad 3-ply bot, maybe. Right? It has bad eval. Eval is very crucial, right? And this will be something to discuss, actually, right? When you make some sort of game playing bot, the evaluation function is crucial, right? So you have two things. You have the thinking part, the apply, right? How deep do you look, right? I did not make 4-ply. With 4-ply, you get 256 times 256 to the 4th power, right? That's quite a bit. That's what 65,000 to 2nd power to square. 65,000 square is what? Is that 60 million? No. How much is that?
Just a lot.
That is 2 to the 16th to the 32. That's 4 billion, right? 4 billion. Yeah, that's 4 billion, right? Yeah, 4 to the 16th to the 4th is 4 billion, right? That's 32 bits, right? 2 to 30 seconds. Okay. So again, if you, so I'm leaving you extra time, so if you have any problems or anything on Thursday, we have some little bit of time to fix things, right? Because I know most of you already have something working, right? More or less, right? Some of you are playing, do it tonight?
The battlefield today.
Yeah. You are ready, you're ready.
I am.
Okay. Super. So beat Martin's bot, right?
So wait.
Try.
Industry benchmark.
A new game, so we shouldn't start a new game when.
No, okay, so let's do this again. So, this is the game, handling game ends, right? Black hole or draw, game ends. Your bot should then start a new game and make another start request. That's my idea, right? So you keep making new game requests until somebody tells you to leave.
Okay, sure.
Sarah tells you to get out, right? So the idea was to make it too easy for you. You don't have to think about that. You just make new game until you are not allowed to make any more games, right? Yeah. Okay. All right. Let's talk about one of my favorite topics today. Right. So our talk about the basics of machine learning. So 18th chapter, multi-agent decision making is interesting, but machine learning, of course, is crucial. So this is sort of starting this again deeper look, like at of course the current state of the art. But machine learning has been around. But of course, so what's happening? How do you know about yourself? When are you learning, right? When your performance improves, right? You're not learning if you're getting worse. I mean, in terms of psychology, of course, when we learn something, it could be that for a moment, we are not improving, we are getting worse.
Yes,
there is such a thing. But in general, of course, our end goal is to actually get better performance by some sort of metric, right? So in this case, machine learning refers to this agent, right, is actually a computer, right? So you need to, so what do we need? So basically we'll need some sort of something to learn from. You need some data, right? Of course, that's a classical thing, which basically machine learning is sort of, you can't really have machine learning without any type of data, right? So, and of course, you'll need to get some feedback from this data, some ways, right? This is very general right now. So, we cannot, the basic idea is that we don't have, we're going to be building a model. We're going to be building a model, right? And we are not going to write the rules like, for example, making a bot, you probably implement, I know some of you might be actually doing some deep learning, but mostly you are doing rules-based. You are your brain, right, or you have communication, right? You provide the rules how you should act, basically, right? Heuristics, right? But machine learning is that these rules come from this process of learning, right? So again, because here's an example, for classical example, facial recognition. For a long time, of course, you know, there were some software that's still around. How do you recognize a face, right? Whether it's a face or not? I mean, you could come up with a set of rules. Maybe you need some, you know, have a picture of face, right? It's maybe brighter. You can come up with some set of rules. What makes a face for the picture of an image, right? But you cannot possibly predict all possibilities of what makes a face. Maybe some you have a, you know, rakurs, what in English? What do you say rakurs in English? Side, a face, view, maybe no, it's a different word. But anyways, but basically, if you are looking at different ways, right? What makes a face, right? Again, coming up all the, you know, of course, they also account for all different races, for genders, and so on and so on and so on, right? And of course, hairstyles, and you know, glasses, right? So you could start writing rules, and, you know, but you'll be spending your whole life, and you will not finish making all the rules. So the other big approach, of course, is you provide examples of what is a face, so-called label data with spaces, right? And your machine learning, right, will be able to learn what is a face, right? Learn means it will be able to classify face or not face. For example, very simple binary classifier, of course. Right? So this is just one of the basic things, right? So today we will not talk about something called deep learning. That's for future chapters, a couple chapters. But basically, this whole big field, right? So let's look at some of the technology. Supervised learning. What does it mean, supervised learning? This means, or examples, we are providing, for the training process, we are providing already pre-labeled data. We have some sort of, usually with numerical data, with so-called features, and we have the answer. We provide the answers. This is a face. Maybe I'll show you maybe picture of, for example, list numbers, digits. Data set, for example, just a simple example, for example, I don't know, a very famous one. Over there, it looks like this from, oh, it's, well, at least it's not taken down yet, thank God, right? We never know, it's America right now, right? Yeah, so it's still available, right? National Institute of Standard Technology. I will not be surprised if it's taken out, you know, in a few weeks. You never know, right? What's happening? But basically, right? Maybe I'll show you the Wikipedia what it looks like, right? List digits. Wikipedia, wiki here. Yeah, it's basically a database, right, or something like this, right? Right. So, right. I believe it's 28 by 28, I believe, or yes, 28 by 28 or 32 by 32. Very small, tiny pictures. And of course, so how many features does 28 by 28 you have? 28 by 28, and this is black and white. I believe this is black and white binary, meaning it's just a black pixel or white pixel, right? So we are providing each, in this particular case, we have multiple rows of this. So think of this each picture as one row of data. Let's say 28 by 28, very tiny picture, right? So we're providing 28 to the square. That's 576 data points. Those are our features. And we have an answer. What's the answer? It's 0, right? That's the answer, right? That's what they're trying to learn. That this is a 0, right? But to do so, our dataset contains 576 data points, right? In this case, you can think maybe the grayscale, then you have a, you know, You have a byte, for each feature, could be binary, yes or no, or could be a color. You have a three bytes, red RGB, maybe 4 bytes. You have RGBA, right? But so 576 features and one answer. So of course, labels generally are single label. There are multi-labels, but generally the basic task is single label. So this is well, you have 10 possible answers, right? Right. So this is one of the early successes of machine learning, right? How to recognize digits. This is a digit, right? So that's the basic idea, right? Right. So that's supervised learning. We provide answers. Now there is also something called unsupervised learning. This means you are given some data, but you don't have any answers what it is. So what can you do then? Might be a question.
From experience.
Yeah. Well, yeah. Of course, you can do. Okay, I'm going to label. Okay, that looks like 0. Okay, that's 0. But then I'm going to go and then do supervised learning. But sometimes you have so much data, you don't have no idea what it is, right? Classical example would be supermarket. Supermarket responses buyer data, right? And you want to determine what kind of buyers they are, right? But you don't know, right? There's data privacy laws, and of course, you are a marketing manager, right? You want to say, okay, these are like good students. They want maybe, I don't know, you want to give them discount on computers or something like that, right? So you want to say that these people buying something are students. You don't know they're students, right? You don't have the labels. Can you do that? Well, you have enough data, you can actually do something called clusterization, which is a form of unsupervised learning. So clusterization, you basically put stuff in boxes. Box A, box B, box C, box D, right? You provide the answers, but you don't know what the answer is. Then you say, okay, then you go back to the data. Okay, box C look like students. Box D look like retirees. Box E looks like kids, right? And so on and so on and so on. So clusterization, or of course also to be used for anomaly detection or fraud detection. Okay, these are not legit, right? They are actually, fraud, right? Something like that. So unsupervised learning. So you train your data without labels. So also should be something called semi-supervised. So basically hybrid, right? You also train it on some labels, right? You have some label data, also you have a lot of unlabeled data. You also want to use that. That's a hybrid approach. Also, there's something called reinforcement learning, right? You give it a sort of evaluation function that gives feedback how well this model does. That's called reinforcement learning. So those are the types, like one way of type separating. So key concepts here, and again, you'll see this over and over and over. So data set, that's what we are learning. So typically, we divide them in 2 parts, at least 2, maybe sometimes 3 parts, training and testing. So why do we do that? Well, we'll talk about something called overfitting. There's a problem with that. That's why you don't train your model on all the data you have. Typically, you leave about 10-20% for testing purposes. Why? You want the model not to have the full knowledge, right? You probably again heard about these days how sometimes like LLMs, like if they know the answers to the exam, and you test it on an exam, right? It knows the answers, like on a programming exercise, right? And that basically is an example of data polluting, basically. It's kind of, you can say cheating, but it's basically not, it makes the model less useful because, right, if you know the answers for that particular problem, right, for that particular 0, right, we don't care if it knows exactly about this 0. We care it knows about my 0, my other 0 is recognized, right? Because if there's something which is not part of this data set, right? So that's the idea. Look at different ways of ones, right? Because maybe you have a different way of writing one, right? Maybe a different approach. So that's what we care about. So we'll talk about training testing. There's also something called cross-validation. So features. So features is we have one data point. Maybe it could be, in this case, this is a picture. It could be an audio file. It could be a text file, right? We will convert it to numbers, a vector of numbers, right? It could be a multidimensional vector, of course, it could be a matrix, it could be a tensor, right? But But that's the basic idea. That's what we learn from, and we have the answers. So labels are the answers, right? So, on the model is, that's what gives us answers, right? So this is some sort of mathematical representation. This is a very wide, kind of loose definition, right? There's all kinds of models. In fact, maybe I'll give another one. All right, here, all models are wrong, but some of them are useful, right? All models are wrong, but some models are useful. Yeah, some statistician. This is basically true, right? So basically, so idea is that basically we are not, when we are training our data, right, it's inevitable there will be some edge cases, right? Again, a simple example. Right, we try to predict whether something, for example, this one here, right? This here is number 7, right? The model answer says 7, right? But I think you make a pretty good case. It's kind of like almost like a 1, right? Can you see this in the back, right? It is bigger, I mean, it's bigger, right? You can make a case that this is number 1, right? Not really, but yeah, more or less, right? So 7 and 1, right? There might be, people have different ways of writing 7s and 1s, but it's close enough. So what about other digits, right? So 5 and 6 is this 5, right? This is 5, but it's pretty close to 6, right? The key point being that even in real life, humans have problems classifying something, right? When I'm reading some old writing, some old handwritten writing, your own mental model may not be able to classify, or own neural net may not be able to classify it. So, okay, so training is when we build this model, we fit the model to our existing data. And inference, this is again, you probably heard this word all the time. That's when we're doing inference, like when you are using ChatGPT, when you're doing LLM, that's what you're doing, inference. You have an existing model of the world, right? And you are trying to make a prediction. What is your next token, right? And so on, right? You're getting new. So very typical, so these are typical terms. You see them all the time. Okay. Now let's move to some common algorithms. These are not neural networks. Those are the new hotness. Well, because they're hotness, but that's where all the big research is being done, right? But there's some old standbys, something called linear regression, actually comes from statistics, known from the 19th century, even older, right? There's also something called decision trees, right? Also very cool. And I also really like decision trees because they are one of the few machine learning algorithms which you can, as a human, can see how they work, right? That's very rare. Most of the machine learning algorithms are, you can only check the results, evaluate the results, do they work, right? Do they work on your training data, do they work on your testing data, or your validation data, but you don't know exactly how they work. That can be a problem, right? So, because you say, oh, why should we, give a, loan to that person? It might be a legal requirement to provide a good reason, right? And if you say algorithm told me to do so, right? That's not cool. That's not cool, right? So, so we need to evaluate, right, our results. So how would you evaluate your model? Well, let's say this digit prediction model, right? You give it some pictures, you have your own data, and basically you give it 10, you give it 100 digits, 100 pictures, and it gives you 87 are correct. Those will be for all true positives, right? And the rest would be, of course, false positives. That will make a mistake, basically, right? So one way of doing it is something called accuracy. There's also precision, deals with false negatives, the recall, the F1 score, which combines them, right? But easiest one for now is accuracy, right? How many did you get right? Usually percentage or ratio. So something accuracy 0.99 would be 99 out of 100 were correct, right? And that one was not correct, right? So that's again something you'll need. Again, otherwise, without metrics to evaluate, you're not really doing anything close to science, right? Now, overfitting and underfitting. So again, very common terms. So overfitting. This means you provide training data. It works perfectly on training data. We give it other data outside, real world data. It does not work well. So this is a classical example of overfitting, meaning you train it too much on this training data, but it does not generalize to actual other data. And the thing is, it's extremely easy to overfit. In machine learning tasks, it's very easy because you can make a mathematical model of any type of data, right? There's John von Neumann who said you can fit an elephant in like make a function with 5 parameters, and you can draw an elephant, right? Basically, right? You give it a function, some data points, and you can make a function which will draw an elephant, basically, right? And so what does it mean is that no matter what kind of data you have, you can come up with a model which exactly fits that data, but it will be useless outside the data. And that's also another thing is underfitting, right? Meaning you come up with something extremely simple, right? Like that underfitting would be the weather prediction model which says, tomorrow will be same weather as today, right? I mean, I told you about 19th century, it worked pretty well, right? Today it's kind of warm, tomorrow's going to be still warm, but again, as we know, more sophisticated models will know that in 4 or 5 days it's going to get colder, right? So I think so, at least. I think that right now that's a model prediction, right? That's the inference, right? So underfitting, right, your model might be too simple, right? Always bet on black or always answer A, right? That's a model, right? But not very, not going to generalize very well, right? So, yeah. So, improving model. Again, these are all terms. So, feature engineering, right? This means is we have some data and we create new features out of this existing data. We modify existing data, maybe combine some new ways, right? And come up, maybe also we obtain some new data, but basically usually it involves using existing features and existing data points to create some new data out of that. Also, regularization, right, means of course, typically we have, our parameters have a very wide range, maybe we have some normalization settings. Also, many machine learning algorithms have so-called hyperparameters. So what are hyperparameters? So these are, think of, okay, your machine learning algorithm is kind of like a black box. You feed it some data, and then you can have selection of things you can tune, right? Some knobs you can twist, right? Some parameters, like how much, like maybe how deep you want to go, how many ply deep, for example, or how many these other parameters will be vary widely depends on algorithm. There could be, what we call decision trees have depth and also some extra parameters for choosing the features, how many features to use, for example. It might seem silly, but it's possible. So, so forms of learning, right? So these are all general terms. You will see these over and over in any machine learning. These terms will come up again and again, right? So, we can enhance any type of machine learning can be applied pretty much to any task, right? You can overuse it if you want, right? So, as long as whenever you have some existing data, which you can transform into some sort of features, numerical data, right? Then you can make a machine learning algorithm. So the question will be how much data do you need, right? Maybe I'll show you later, but if you have there's something scikit-learn, it's a nice library, Python, right? Cheat sheet, right? It gives you choosing the right estimator, right? So this is nice. Your machine learning in one picture. This algorithm, right? Which what to choose, right? So basically, you see these multiple tasks, right? Basically 4 tasks. Maybe only it's bigger. Maybe it's bigger. Something bigger. Oh, here you download. Oh yeah, there, no, that's nice. Yeah, it's an SVG file. So you basically start here. So how much data? If you have 40 data set, 40 answers, you only get more data, right? You need to get more data basically. So yeah, so machine learning really starts with 50 samples or more, right? There's statistical reasons. I mean, otherwise you will not really get useful model. Of course, many really good algorithms get really good and you have a lot of data basically. So maybe bigger zoom,
but
maybe
yeah,
okay. Do you see this? I can see. Can you see that one?
I can see that. Yeah, but I just like.
Okay, come on, the rest of you guys. Yeah. So this is a really good sort of gives you a really quick overview what we're talking about machine learning. Right? So classification. Is it hot dog or not? Yes or no? Is it 0, 1, 3, 4, right? So notice how if you have less than 600,000 or more, that tells you different algorithms to try, right? Clustering. So do you have labeled data? If you don't, that's clustering, right? You just have box A, box B, box C, but you don't know what it is. You have to decide yourself what it is, right? Classification, you will be able to test on particular answers. So regression, this means you are predicting something floating, meaning numeric, right? So what's the difference? Because again, so
I'm just thinking about the one that goes to tough luck.
Yeah. That's it has two ways to get tough luck, right? Yeah. So predicting quantity, just looking, no. Predicting structure, tough luck, right? Number categories, no. Less than 10,000 samples, right? Yeah. So idea being that if you don't know anything about your data, right, you end up with tough luck category, right? Yes. Yeah. That's sometimes think, okay, I'll just throw it to some. I have a bunch of data, I have no idea what it is, I'm just going to throw it in, right? And my machine learning algorithms tell me what I have, right? No, that doesn't work like that quite. Usually, you have some data, something gives you, a file, it says, okay, make sense what it is, right? Well, you can make some hypotheses, right, of course, and you can test those hypotheses, but you won't be able to, get there. So, regression, right, again, you have answers, right? You have answers, right? So, regression will be predicting numerical data. So there's differences. So A, B, C, D, right? Or 1, 2, 3, 4. Sometimes this can be, especially when you're starting out, you might be saying, okay, you're predicting category 1, category 2, category 3, category 4, right? It's numerical. Not really, because if this is 1, 2, 3, 4, you want to, they should be comparable, right? More or less, right? Numerical. But if they are completely independent, right? Then it is actually classification, right? Just because class 1, 2, 3, 4, right? Because numbers, could be any arbitrary numbers, right? Any arbitrary labels, it is a classification. If those are real numbers like prices or time, price, number of houses you can afford to buy and so on, right? That will be, of course, regression task. And this part here, actually, right? This is more like a data science, that analysis part is basically sometimes you need to do change your data shape. You have 100 dimensions or 1,000 dimension vector. You only want two-dimensional vector. Why? Because you want to visualize it, right? And you don't have good tools to visualize 100-dimensional vectors, right? You only think in 3 dimensions, right? Visualize things. The 2 dimensions are very popular for visualization. Okay, we'll get back to this again in a moment, later on in this course. So a self-driving car learning from human driver might learn how to brake based on what? Right, it might need to recognize objects, right? Camera images, right? Learn the effects, right? And of course, it adjusts the function. It can adjust the function, right? So of course, machine learning, right? You can optimize, software development, of course, right? All right. So idea is originally you have very minimal knowledge, right? So that's an assumption, right? So again, let's look at this example here. So we'll make this Can I see this? Can I show this picture? Oh yeah, let me open this up. Yeah, let me open this up. Show this to my GitHub. Yeah, I hope so. Yeah, all right. So this is the book. So we have some data, right? One, this one, and this is two, right? Well, so this is underneath. There's a whole bunch of data, right? We took a sample, right? Maybe 80% sample, I don't know, right? And if you apply a linear regression algorithm, right? This is numerical data. We will be able to come up with a model, right? Which is just a simple linear function, right? That's a mathematical model, right? And that might be exactly what we want. It's the most popular one, right? Of models. But you could also come up with some sort of sinusoidal function, right? Which has some regularity. And again, if you have some additional data, there's some sort of seasonal patterns in the data, right? And sinusoidal function, right, might make more sense. So this part here, right? What is this model? This is like a really silly model, right? So what it does is it draws little lines between points, basically, right? The only is bigger, right? So you can see piecewise linear. So it draws a line. Okay, it's possible. This might be what you want, right? Meaning there is a. This means if you have some sort of data x comes, right? So if you ask answer, what should x for let's say value 500, it will give you answer here, right? Exactly here, right? So you have a model, again, which one of these is best? Well, you need to test it on the actual data you use for testing, whichever works best. How about this one here? This goes back to Mangione Newman's idea. Yeah, you can fit an elephant to any, right? Make a function, right? There are elephants, so you can come up with really fancy polynomial function. This means degree 12, this means there's some x to the 12 somewhere, right? And it fits perfectly, right, for that data, right? However, most likely your testing data is going to perform much worse than any of those, right? Why? Because by creating this complex function, you end up with huge peaks and valleys, right? And it is not going to represent your data. The error of the UML function will give you more errors than these other ones. So, and the book makes a point that if you have slightly different, it looks very similar, right? But not quite, right? It's very similar. So, idea you have a data set, you took some different points. You have a sample, random sample, and you apply. Well, the linear function, it might have slightly different slope, a little bit, right? Your sinusoidal, yeah, you'll have a little bit of irregularity. Your piecemeal, again, will be a little different, but the degree 12, right, which will give you the highest accuracy, that's the problem. See, that is the issue. Notice, you can see here, right, this gives you some errors, this also gives you some errors. Well, this does not give you any errors, right? But, no, I mean, so these two don't give you any errors, right? So, right, you see there's no errors. It fits exactly on a training. If you test it on a training data, it will say 100%, 1.0 accuracy, perfect, right? But that does not mean anything. Until you give it some testing data, right, you will see how it performs, right? So, again, there's lots of processes in life, in nature, which are linear in nature. That's why usually everybody starts with linear regression, right? So, again, so hopefully you can see how slightly changing this is,
Isn't it possible to develop a better 12 polynomial?
Yeah, it is possible, but the problem is, this is the data you have, right? You're given this data, you try to fit it, right? So, fitting by itself means you try to fit it as close as possible, right? And of course, here you get 100%. It's perfect, it fits perfectly, right? It fits perfectly, but
you could hypothetically make a precise one that's better than sinusoidal, but not as precise.
Yeah, but again, you will only know that when you use it on data it has not been trained on, right? That's the whole point. When you use it on something, the model does not know.
You're basically, not that you describe the relationship, but you just assign the most closest line to your existing data.
Yeah. So, by the way, it's interesting. This is not also this often not used. So this is very tempting because it fits perfectly, right? There are lots of small lines, right? But first of all, what's the problem with this one here? I know the problem is well. And also this problem is these two, but this problem is these two. Okay, if it's tight range, it might be good. The problem is the weird stuff. You could do. I have some notebooks on this actually. If you go like maybe here, right, outside, your 12 power polynomial will be all over the place, right? And it will be somewhere really off, right? Most likely it will be nowhere close where you want to be, right? So that's the problem with these high-power polynomial functions, right? Unless you have a suspicion that your real-life process is modeled using 12-power polynomial, is not going to be the answer, right?
What's the process though?
Yeah, I don't know of any process which uses 12-power polynomial life, right? Yeah, I know logarithmical process, linear process, right? Sinusoidal process, right? Yes, but quadratic process maybe sometimes, but 12 degree, very rare. I don't know. Right. Maybe if you come up, right. So that's it's very tempting. I know myself too, right? The question is a good one because also I thought, we can play around with functions. You can make functions do anything, right? So what I was talking about, function to draw an elephant. I think it's actually, not with single parameter or something came up with look at this here. Something came up with single there is function, right? That's an elephant, right? Something came up with single parameter function without an elephant, right? No more or less an elephant, I don't know. I guess it is, right? So what's the function? Let me see. This looks like this function, right? X how can we modify this?
Put it in a Desmos?
Yeah, it just says there's a whole bunch of arcs in stuff. Let's see the final function looks like, right? Yeah. I think he published a paper a couple of years ago regarding elephant, right? So, but so this is the backward theme. So this is a polymetric over adjustment, right? You start doing stuff, right? So let's look this here, left side, right? It fits nicely, and then you go slightly outside, right? Check this out here, right? And your nice model starts behaving like a mess, right? Because of course you do not have data on this, right? But you have the data and you have nice prediction, right? You can come up with a function that describes your data perfectly, 100%, right? But whether it's useful, that will only your test data will show, right? So if you are only going to do back testing, you're not trying to predict future, which is very rare, right? You usually want to predict future, right? So then of course this function might be okay, right? Maybe it's probably the previous data, right? Some data points you did probably the same thing, but in future, right? There's this happening, but your function is going to be useless, right? I mean, near useless, right? So this is a pretty important point because you come over it again and again, and it hides this overfitting hides all over the place, right? Because our goal is for machine learning is to actually make predictions, right? Useful predictions. Because of course, if you try to make a function to draw an elephant, right? That's a different task. We can do that as well. Okay. Let's see what we want to cover today. Supervised learning, right? We basically want to discover a function that approximates a known true function, basically, right? So we have, a hypothesis is going to be very wide, right? Very wide change, right? Maybe hard to come, right? So we wait for taillight, right? So, problem, right? So, example problem in the book is deciding whether to wait for a table at the restaurant, right? Okay, so you have a Boolean, it's a binary classificator, wait or not wait, right? Choice. Wait or, go home or whatever, right? We are, for now, not waiting includes going to another restaurant or going home or going to bed hungry, right? But we'll wait, right? So we have a bunch of features. Alternate, right? We have a suitable restaurant nearby. We have if the restaurant have a nice bar to sit and drink some drinks, right? Also a good feature. Is it Friday or Saturday? Are you hungry? Your level of hunger, right? Patrons, how many people are in the restaurant? Price, right? Raining. Do you want to go outside in the rain, right? Reservation, right? Did you make a reservation, right? I assume if you made a reservation, you're probably going to wait, right? Unless there's some really bad thing. So type. So that's another thing, yeah. French, Italian burger place, right? And you're probably not going to wait for a burger, an hour for a burger, right? Probably. Right? How about Ausmir kebabs? I know it's not too busy, but then I know in Agenskalna, it's very busy actually. I know there's always line there, right? In Agenskalna. Here it's not so busy, right?
It is busy.
Is it busy here still?
We wanted to get it today, but we had to wait for half an hour.
Oh, so even during midday it's still busy. Yeah. Maybe I'm sure you can monitor, you should have a sensor outside here and monitor the crowds, right? How many people are there,
You could. I'm not sure if that's legal, but yeah.
No, if you assume you apply an algorithm to blur people, you're just counting heads, right? So maybe somebody brings an extra dummy head or something, it doesn't matter, right? So
if you put a security camera, then it will be legal.
It will be legal, yeah. You're gonna, or if you have to give it to there's an organization. If you have a security camera, you apply. If it's in public, you have to provide a reason that you are collecting data, and it flies, right? Right. So
I mean, but doesn't Google have something similar? In Maps, they have not too busy or...
Yeah, they do, but how do they collect, of course, right?
Based on the phones active.
Yes, Android collections and iPhone collections and things like that, right? Yeah.
There was this guy who put 30 phones.
Yeah, you see it's funny, made a traffic jam over bridge. Yeah, it's really good. In fact, sometimes when you're driving, you see sometimes Google Maps says there's a traffic jam, but there's no traffic jam. So I'm wondering if there's a guy in Latvia too taking some extra phones with him, right? Maybe it's one of you, I don't know, right? So this is again an example. Right, oh, come on. Okay. Okay, yeah. So we have, so these are rows of data, these are index, right? So there's 12 restaurants, right? And look at this, this is very typical machine learning data set, right? You have some binary attributes, yes, no, true, false, right? You have something, some full, none, categorical, right? And of course, this becomes an issue. Yes, no, 0, 1, easy. But how do you do some full, some none, right? Completely empty, burger place empty, right? But there's nobody eating, but they say it's not, you can't even get a burger. That's kind of really suspicious, right? I would not want to stay at the place which is empty. You can't get, you have to wait, right? I would probably leave unless it's right? Because you don't have the social validation, right? You don't have anybody sitting there, right? So, and this is an issue here. How do you encode this, right? Because you have none, well, none's full sum, it's pretty easy. Well, you can probably say, okay, 0 will be none, 1 will be full, 0.5 will be sum. That might be okay, that's a good assumption, I think, right? Price, same thing. You can say, okay, cheap will be, let's say, I don't know, 0, 0.1, right? Completely free would be 0, right? Cheap would be 0.2 maybe, I don't know. 0.5 would be $2 signs, 0.75, 3, and 1 would be 4. And this again, at each step, this data preparation step, it might be your assumptions, you change how you prepare data, may make a big difference later on. Okay, rain and reservation, it's fine. And yeah, and then the type. And this is the hard part, right? How do you encode this? You have a French, Thai, burger, and Italian, right? And this is where you can say 0, 0.25, 0.5, and 1. Not really, right? So what do you do? Does anybody know what you do? What's typical thing you do? Anyone? Any idea how you solve this problem? This is pretty common problem in machine learning. Maybe some of you have done this before.
Yeah, I have. No, I'm not going to mention my solution, but yeah, I have encountered this one.
Okay.
But no, my solution is just not to deal with this column.
Okay, ignore it. Okay, since you guys are smart, so use something called one-hot encoding.
I have something I considered was just putting column for each.
Yes, this is called one-hot encoding, right? We'll talk about this maybe later, maybe not. One-hot encoding. So one of them is hot, the rest are not, right? So this is so basically this, right? So only one bite, right? National lunch posting, yeah. So apple, chicken, broccoli, right? So you do this basically, right? Apple 1, chicken 1, so each gets its own binary yes, no column, right?
The question is whether something suffers from that.
No, to me,
or whether it's like doesn't the performance or something?
No, of course it could be
performance suffers.
Yeah, of course. If you have 500 different categories, you need to make 500 flags, right? But the idea is this: you want to. There's no numerical relationship between a burger place and a Thai place, right? Well, there might be some, but it's not in general. Assumption is an apple is different from broccoli. They should have its own feature, right? They become its own feature, basically, right? So you kind of extend, right? Make one hot. Okay, right. So on the output, you see, and these are your labels: yes, no, And this is then you feed into your machine learning algorithm, and you will have a model what to do when you go to a restaurant, and you feed it in. Okay, it's a Thai place, it's full, it's expensive, and so on and so on, right? And your model will give you an answer, right? And it could be a very good answer, it could be a horrible answer, I don't know, right? So it will depend on the model. So let's proceed. Where's my one hot, okay. Yeah. So decision trees. Maybe we'll do a workshop on this. This is very cool. So decision trees are like playing the game of yes, no. There's a game like you basically make a bunch of yes or no answers. And that's all you're allowed to do. You're allowed to only say yes or no. So you make a split at each question. You ask about some feature. In fact, you can ask about the same feature multiple times. But you can say, okay, is your patient's temperature over 37 degrees, right? And you say, is his throat hurting, and so on? Is his tooth hurting? Is he scratching himself, and so on and so on? Yeah, is he male? Is he female? Might be important, right? Is he under 18, right? And you maybe say, okay. Otherwise, later you ask, is he under 15, under maybe 10? It might be different, right? So this is decision tree, and this is basically only yes or no answers are allowed, right? So the beauty of this approach is that it can be visualized, it can be understood by also somebody, sitting in a factory who doesn't want to think at all, right? He has a checklist, okay. It could be like a computer basically, and so give the answer basically. But each step gives you clear-cut instructions, right? So you come up with something like this again. So this is right. You end up with this. Okay, so you check. In fact, here, of course, you can say 3, but okay, because one hot, you can use it one hot. So no, right? So if there are no patterns, right? So if there are no patterns, that's very suspicious. So this model, this particular decision tree will say, don't wait, right? So if there are some patterns, you wait, because you estimate, okay, this must be okay place. People are eating here, right? But also, interesting enough, okay, this is an example. You don't even check for any other information. You just wait because it looks like it's half full. There's going to be a place soon. You don't even wait for estimate. But maybe probably the next step is ask for estimate. You ask for an estimate. Okay, it's over 60-minute wait. That has to be a really amazing restaurant to wait over 60 minutes, right? So, then it's 60s. So then, okay, 36, you start thinking, okay, is there any alternate nearby? No. Do you have a reservation? Then you wait those 30 minutes because you have the reservation. So you are guaranteed the spot. You have no reservation? Okay, you check. Do you guys have a bar? They have a bar, right? That's, I'll wait, I'll get drunk. Meanwhile, I don't care anymore, right? So, in fact, this is actually, I've had the experience not getting drunk, but meaning, but a bar, you have to wait. If you're going to the restaurant, this is an important country, there was a big wait, but the bar was, they let us go to the bar, but actually it's there, they serve food there as well. That's like the best life hack ever, basically. Because they gave us extra drinks, plus the food, basically. We got extra drinks, they're making drinks, they gave us the leftover, whatever the cocktail they're making, basically, right? So it was an amazing deal, right? So, obviously a big factor, right? So Friday, Saturday, right? So again, of course, if it's Saturday, Friday, you probably, again, you won't go out, right? You want to have fun, so that's probably you want to wait. No, if you're hungry, right? If you're not hungry, right? Wait, you're not hungry? Okay, yeah. So if you're not hungry, you wait. I guess you don't care. So if you're hungry, you look for alternates. Then no alternates, you have to wait again. If it's raining, there are alternates. You check if it's raining, right? Maybe you'll go out in the rain. If it's not raining, you'll go find the alternate. Maybe it's better, right? So this is called decision tree on the basic machine learning algorithms. This is one of the basic ones. And again, it's one of the rare ones where you could build up something humanly understandable. Of course, the decision tree could be huge, but at least you'll still be able to follow it, right? At each step, you have a certain set of actions you can take. Now, how does it build this step? How does machine learning algorithm build this? Of course, in the process, again, it's a very complex process how it builds these questions, right? But of course, it tries to minimize the error of your given data, right? It tries to come up with an answer. 1 second. Yeah. All right, so is everyone pretty clear on this decision tree? Okay, all right. Now, let's move on. Almost finished, I think now. Yeah, so still the code, we have a nice scikit-learn, has a really nice library for this, right? So, we're going to go into the actual attributes. So yeah, obviously again, this decision tree, if you ask so many questions, you can come up with the decision tree which is perfect for this particular data set, right? Right? It will give you the exact answer, right? For these 12 data points, right? But again, that might be fit perfectly, but does not mean it might not be a useful model, right? And again, it might not answer what to do with time food, which is, when you're hungry, right? You see, this is 12 data points. That's nothing. You need probably 100 restaurants, right? These cases, right, to get something useful out of this, right? So, because you have a lot of features, right? So this means there's a lot of things to change, right? So this model, which you learn from 12 data points, is by its design, you're not going to be able to always give, accurate answers from this, right? So, now, yeah, and of course, we have some things. Of course, a lot of issues can arise when you're doing machine learning. Most of the work is in data preparation, cleaning your data, because you might have some missing data. What do you do when you have missing data? What options do you have?
Ignore.
Yeah, that's one. Yeah, that's a common one. You have a million data points. You can probably make a good choice. I have five rows of data, but I'm missing some entries, right?
So substitute with the 0.
0, very dangerous. It's possible. But 0, if it may have meaning, right? That's possible. I'll tell you, but there's something better than 0. What do you do? Okay, so what happens is there's something maybe this. You don't have you have a sort of limited set of data, and also you have issue might be this, that the missing data comes from specific maybe all Thai restaurants, right? But you want to keep those Thai restaurants, but they don't have any data about raining that day, right? So what you can do is you interpolate, meaning you make you choose the most commonly used option for that day. It was raining, maybe, right, or maybe not raining, for example, right? So you don't say 0 by itself, not raining, right? You make an informed choice of what the likely answer. So you sort of like, you make up data, right? 0 is also making up data, by the way, right? Yes. So, of course, you can also say, you can sort of ignore that column, right? That would be another option, right? Just ignore that whole raining data for the whole, for whole data set. Maybe, that's also possible, right? That's kind of hyperparameter tuning, right? But yeah, if you want to use it, one of the options is something called interpolation. Interpolation is something you sort of make a model for that feature, right? You sort of make a prediction what this data should have been, most likely. And you say that's kind of silly, right? But no, assuming other data is, so to say, legit, right? It's actually useful. That might be an option. Of course, again, easiest, if you have a lot of data, throw it out. Again, the reasons for not throwing out data is if they come from a particular subcategory. If they're like sort of random, right? Seems random, right? You have a million data sets and you have some, some dirty data, which is not useful, I don't know, 100 data points, right? They're sort of messy, but they all come, so, maybe some, I don't know, OCR errors, maybe scanner didn't work, or I don't know. And then you throw it out, but you, of course, you have to document this, of course. Because throwing out data without any reason is dangerous, right? So that's how lots of studies, lots of algorithms, get broken. Because oftentimes, like you're building your self-driving car, right? And you don't have data for, I don't know, something outside the city, right? And you have missing data from, you don't have a, I don't know, traffic light situation outside the city, for example, right? You throw out all the data outside city, and of course your robot car will not drive very well outside the city, right? It's probably gonna, especially if it encounters a traffic light outside the city, right? There's gonna be a problem, right? It happens sometimes, right? So, right. So objective is to find the hypothesis, the model, right? And to most accurately predict future examples. That's what we are doing, right? So, again, I mentioned this cheat sheet, right? This is practical. This one is very practical. So it just gives you, of course, there's many more algorithms, right? But for now, these are some of the basic ones, and again, which are available in this library, right? And give you sort of good starting point. If you start doing this with machine learning, I highly recommend using this scikit-learn library. Again, this is Python library. Of course, underneath, it's not in Python, it's of course some lower level algorithm, lower level language. So, lots of ways of model selection, right? Yeah. So, you're trying to basically minimize error rate, right? The loss rate, right? So, again, there might be this true function is not really, you cannot have it, you cannot come up with actual, it's impossible to come up with a true function for, the actual function. Because, it does not exist actually in real life scenario. You want something that's close enough, right, basically. So yeah, regularization, right? So basically you want to minimize maybe some feature, like, for example, you're trying to predict. Okay, let's look at this example from the book. I mean, this one here, right? So, right, so this part here, right? It's numerical, right? Right? How long you have to wait? So issues, and these are all 0, 1, 0, 1, 0, 1, right? Most, this may be 0, something floating point, right? So issue is, you have to be very careful with this type of data. Issue is that this estimation data might be, if you leave it as is, from 0 to 60 or 0 to 120, right? It can dominate the model, meaning the rest of parameters won't matter because they're 0, 1, 0, 1. They're too small, right? So what do you do then? You know what you do? You normalize it to 1. So you divide by max. So 120 or 160, you divide by 60, right? So 0 will be, this will be maybe like 0.16 or something like that. This will be 1, right? You normalize. So this fits with another parameter. So they're all equally important. obviously, you have to think about this, whether this is actually relevant. Is this, there also could be a judgment call involved. Is waiting time is equally important, but generally, you want your parameters to be equally important. Again, if you want something more important, obviously, usually, the algorithm will be, you can easily add a scalar, multiply by 2, multiply by 4, make something more important. Maybe being hungry is more important than 0, 1, maybe it's 10, right? On a scale from 0 to 10, how hungry you are, right? Maybe that's more important, right? So again, of course, it will affect your performance. And of course, this means you adjust the data set. So this is basically feature engineering, right? You adjust something that normalizes. So I'm going to finish soon, actually. So a couple takeaways from this, right? So data cleanness, data, what kind of how you present the data to the model matters. What type of model matters, of course, right? What kind of hyperparameters we do. So this is what machine learning engineering happens, right? First of all, you spend 80% of time cleaning data, and then you play around with parameters, right? You tune and see which ones give you the highest accuracy, or maybe recall, right? Advanced scores, right? You check the metrics, and the problem is might be that you might be potentially unlimited hyperparameters. Maybe you have like 6 parameters, and they have a range, floating point range. You cannot test them all, right? So it's like looking in the dark, baby. You have to, of course, know something about the particular algorithm. Where do you go? All right? And yeah, so linear regression, we talked about this, right? So linear regression is very convenient, right? It's very easy to do, right? It gives you numerical answer, but only the issue is this is that you're doing it right here. Come on, I'm making a copy. How can I? Come on, I want to open this up. They opened up already. Where is my answer? We are also there. So yeah, so this issue here is that this answer, this linear function, linear regression will give you 4 very different data sets, right? And only so this one is most probably what you want, right? Here you have a nice part, this would be a quadratic or parabola, right? Here you have just a set of data, right? Again, categorical, yes or no, probably looks like, right? And this looks like an outlier, linear, but it's an outlier, right? So you need to before you start using linear regression, you need to know a little bit more about your data, right? I've seen some bachelor's thesis work which use linear regression to predict stock price or something like that. It's highly likely to work, right? And then you'll be very rich very quickly, right?
I read the paper.
Yeah. So yeah, it's very difficult. And of course, linear regression is like the easiest to implement. I mean, you can use it as a baseline. Yes, you can use it as baseline, but probably most likely it might not be the answer. Okay, so we'll look at some other models. Yeah. So one of the answers is sometimes you want to, if you have a very difficult problem, you do something called ensemble learning. You try different models. You do a hybrid approach, right? So, yeah, you're going to do data boosting, right? So again, data collection, right, is the hardest part. And then, of course, you need to explore your data, right? Feature engineering, and this part here. First of all, what are you trying to solve the machine learning problem, right? Are you trying to predict whether to go to a restaurant, right? You need to define clearly what you're trying to do, right? Just don't start blindly working, you don't know what you're trying to do, right? Then, of course, data cleaning, this is 80%, right? So, of course, usually I see people skip this part and they get some existing data, right? But you still need to verify what you have, right? So exploration, right? Knowing roughly, getting some statistical insights, right? You guys take statistics, right? So then you try these different features, select model. You can use the cheat sheet, you can try different models, and see how they perform, right? And deployment, of course, now you can deploy to production, right? So, and that will be, I see, for now. A lot of this could be a whole course just on this, by the way, right? Or machine learning. So we'll cover some specific subsets of this, right? So very, very, how to say, crucial, right? At least for now, learn the terms, inference, models, right? Data sets, right? What they mean. Okay, any questions on today? Idea of what we are trying to do, right? We're trying to predict something, right? What's most important?
Clean data.
Yeah, clean data. Very good. Very good. Then you can do the fun stuff, right? Yeah. All right, that's it for today.